I'm Jordi Verkouteren and I've been working for VMM for over 15 years now. My main expertise is measuring and characterization of particulate matter. Within vacuums, my main focus was the PM data, so that's data validation, data analysis, and data reporting. In this presentation, I'll be talking about the setup of the campaign, the data validation, and the data analysis. I'll finish with a quick look at our fact sheets and sensor scoring system, and of course, the lessons learned. Let's look at the setup first. Here we are on the rooftop of our urban background site in Antwerp. The 3 vented towers you see, that's where all the magic happened. Our campaign lasted for about 400 days and we tested 6 types of sensors with 5 units per type. For the comparisons, we used 2 reference systems. On the left, you see the sensors we tested. On the first row, we have the Honeywell HPMA, the Dialos, and the SDS11. That's the sensor that's used in the sensor.community network. On the second row, we have the plant tower, which is the type that's very similar to the one used in the Purple Air network in the US. Next to it is the Winson and the Chenier PBD60. And on the third row, there are 2 sensors that we couldn't get working properly, so they were not included in the report. On the bottom of the slide, we have our 2 reference systems. On the left, the EU gravimetric reference that collects dust on filters and gives us 24-hour values for PM2.5. And on the right, we have the FIDAS 200, which is an optical monitor that's EU equivalent. I know you're all very hungry for data, but before we start the data crunching, we first need to talk about data validation. A very smart colleague of mine called David made a validation tool that allowed us to validate the 1-minute averages of the sensors. We used 3 codes: 0 for the valid data, -1 for suspicious data, that was data that looked normal but behaved different to the other units, and -2 for the invalid data, which was clearly wrong or impossible. Here are some examples of suspicious and invalid data. We first have a case with spikes on a single HPMA sensor. Second is a period with Dialos data that was clearly all over the place. It was so bad that we took the sensors back to the lab, we opened them up and found a lot of dust and fluff in the optical units. So we cleaned them and then sent them back to the field. Third is a case with an SDS sensor giving a series of maximum signals. The fourth one is a mysterious case where a Winson sensor was giving spikes always on the hour or half hour. So that was probably some sort of electronic interference, but we never found out what it was. And the last one is also a Winson sensor that was giving an elevated signal that started around noon and ended somewhat before midnight during a couple of days in summer. Also something quite mysterious. So after the validation process, we could start the data analysis. I won't be going through all the results of the report, but I'll show you some of the most interesting things. The first chapters of the report each discuss one sensor type. In each chapter, we start by just looking at the data by means of time plots, as the one you can see here on this slide. Then we look at the correlation with the FIDAS reference by making several scatter plots. We also make some plots using the sensor reference ratio, and we calculate the between sensor uncertainty to have an idea of how well the 5 units compare. And last but not least, we enter the 24-hour data in the EU equivalent spreadsheet. This is an Excel file that national networks can use to demonstrate the equivalence of their automated monitors. I'm not going to go into detail about equivalence, but basically equivalence means not the same, but close enough. Here's a collection of the PM2.5 correlation plots, where we have the PM2.5 signal of the FIDAS on the x-axis and the sensor signal on the y-axis. We can already see that the different types behave quite differently. There are 3 units with R-squares above 0.8, the HPMA, the Winson and the plant tower, although the last one clearly overestimates. Then we have the PPD and the SDS with R-squares between 0.7 and 0.8. And the most expensive unit, the Dialos, actually has the lowest R-square, and it also clearly overestimates. Next up is an example of some sensor reference ratio plots. We plot the ratio in function of time to check for drift. We also plot the ratio in function of temperature and relative humidity. Now, especially the last one is quite interesting, because we know that particles grow in size when humidity increases. That's because they take up water. Now, we also know that the uptake of water depends on the type and composition of the particles. So it's interesting to see how different sensors behave. And finally, we also calculate a humidity factor, which is a sensor reference ratio above 90% divided by the sensor reference ratio around 50%. So for the HPMA, that factor is 1.7. But we see quite some differences between the different sensor types. This slide shows an example of an output of the EU equivalent spreadsheet. On the x-axis, we have the gravimetric reference data, and on the y-axis, we have the 24-hour average of all 5 sensor units for a certain type. In this case, the Winston sensor. There's a lot of numbers, but the most important one is the expanded uncertainty at the limit value. That number basically tells you whether your method passes the equivalence criterion, which is 25%. So in this case, the Winston scores 42% and fails the test for fixed measurements. One of the reasons why it fails is because it's underestimating the concentrations. However, the EU does allow you to calibrate your method. So when we apply a slope and intercept correction to the Winston, we see a clear improvement and we end up with an expanded uncertainty of 15%. Now, before you all start throwing away your expensive monitors, I do have to point out that this really is a best case scenario, because we only used one site and we used the full dataset for the correction. I'll come back to the effect of different locations in a few slides, but you can be sure that it matters. And testing devices at different locations is also a European requirement. So the results for PM2.5 were not too bad, but what about PM10? Well, apart from looking at PM10, we also decided to look at PM cores, which is a fraction of particles between 2.5 and 10 micrometers. In the first plot, you see the time and scatter plot for the PM10 signal of the SDS. It's not as good as PM2.5, but it's not too bad. But when we look at the PM cores alone, we see that the situation is a lot worse. The SDS only picks up a few of the PM cores peaks, and the correlation is pretty bad. So the correlation we see in the PM10 is mainly the underlying correlation of PM2.5. So if you really want to know whether your sensor can measure PM10, forget the PM10 signal and look at PM cores. I'm not going to show you the data for the other sensors, but believe me, they were all quite bad. The only two sensors that did pick up some particles above 2.5 were the SDS and the Dialos. And it's probably not a coincidence that those two sensors had the biggest fan. Bigger fans are just better at collecting bigger particles, it seems. Another way of finding out whether your sensor can measure PM10 is to plot the PM core signal versus the PM2.5 signal. For the reference, we see that those two are hardly correlated, and that's what we expect. But when we make the same plots for our sensors, it looks quite different. For the Honeywell, it's actually very obvious to see that the sensor just adds 1 or 2 micrograms depending on whether the PM2.5 signal is below or above 25 microgram per cubic meters. And also the Winston and the Plantower appear to use some sort of simple algorithm and underestimate PM cores. For the SDS and the Dialos, the scatter plots are different, but they're not the same as our reference. So something is still not right, but at least the two signals are not correlated. Knowing that local sensors are pretty bad at picking up PM cores is important when you realize that many people want to use these sensors to monitor local sources of PM that are missed by the national networks. The reason I'm saying this is that local PM is often PM cores, especially when it involves mechanical processes such as construction works, non-tailpipe emissions by traffic, and industrial handling. So, using low-cost sensors to monitor these sources might not be a good idea. Now, it's not all bad news, because combustion reactions do produce smaller particles. So low-cost sensors can, for example, be used to pick up things like wood smoke. Whether they are very accurate for these specific aerosols is something that needs further investigation. but they certainly can give you an indication of the presence of this type of pollution. That was all for the data crunching. Now I'll show you how we translated everything into fact sheets and a scoring system. First, every sensor chapter in the report was summarized into one single fact sheet per sensor type. It gives you 3 main plots and a very short description of the most important criteria that we looked at. Next up, the most important criteria were combined into several summary plots. On the first row, we see the correlation factors, then the humidity factor, and on the right, the between sensor uncertainty, both expressed in absolute terms and relative terms. On the second row, we have the mean bias and the expanded uncertainty versus the gravimetric reference data, before and after a calibration correction. Now, to be honest, this type of info is mostly useful for experts that are involved in PM measurements. So, to translate that technical information to normal people, we developed a scoring system. We took 5 more or less independent criteria, and for each we made 5 categories from excellent to bad, so from 5 to 1. The criteria were uncertainty at the limit value out of the box, uncertainty at the limit value after the calibration, the between sensor uncertainty, the humidity factor, and the data availability in this project, so the total number of valid hours for all 5 units combined. This resulted in the following color plot. Now, when you ask me which sensor is the best one, the answer really is it depends on what you want. Are you willing to calibrate or not? Is low between sensor uncertainty very important? Or is high data availability very important? First, answer those questions, then look at the scores, and they will hopefully guide you in your selection. The 7th chapter in our report discusses the importance of the location of your test site. At about the same time as vacuum started in Antwerp, we also placed 8 Luftdaten units with SDS sensors at VMM monitoring sites. One was at the vacuum site itself, and the other 7 were at different types of locations all over Flanders. As you can see, the results for the different locations are not the same. We see different slopes and different R-squares. And we also noticed that the results were usually better for the 24-hour data than for the 1-hour data. Now at the first location, R701, we had a long period where the sensor had a lower sensitivity for some unknown reason. So that's why the R-squares are so bad. As for the other 7 locations, our vacuum site, which is R801, has an R-square that is quite a bit better than the 3 sites above it in the table. Now what's obvious for these 3 sites is that we see quite a bit of data where the sensor overestimates. We believe that the reason for this overestimation is the local humidity regime. In the first plot, you see the average daily pattern for the relative humidity. Our 3 sites all show quite a bit of data that's above 80%, where we know particle growth gets problematic. The second plot shows the normalized sensor to reference ratios. We use the normalized ratio to compensate for local variations in sensor sensitivity here. In this graph, we also see a high fraction of the curve above 1 for our 3 locations. So that's basically the data where our sensors are clearly overestimating. Now the question is, what is causing this humidity pattern? Well, we believe it's the abundant local vegetation at these 3 sites. And that's why we internally call this the vegetation effect. Now, vegetation is likely not the only thing that can affect the local humidity, but it's certainly an important factor. Anyway, it's something to be aware of, especially when people start thinking about applying humidity corrections. We believe it's essential to have good local humidity data at the exact location of your sensor, just to compensate for this effect. By the way, these graphs also explain why the 24-hour data perform better than the 1-hour data. As you can see, on average, our sensors overestimate in the first half of the day and they underestimate in the second half. So by looking at the 24-hour data, These two effects sort of compensate each other. Oh, and one final thing, we use the relative humidity data from our own monitoring stations. So not from the basic units that are often combined with the Luftdaten sensors, because we know that the quality of those is often problematic. Congratulations, you've made it to the end, and so has my voice, more or less. Time for the lessons learned. First off, no surprise, but no sensor is perfect. Second, validation is recommended, and using 2 or more sensors at the same location can certainly help with that. Third, we see pretty good results for PM2.5, especially after calibration. However, for PM10 the results are pretty poor, and our advice is to really check PM cores, and if you don't have a reference system, at least plot PM cores versus PM2.5 for your sensor. And finally, location matters. Especially places where humidity often gets above 80% appear to be challenging. A humidity correction could probably solve part of that issue, but be sure to use good and local humidity data for that. Okay, so the only thing left for me is to thank you for listening, and of course you can find the report and the fact sheets on the Vacuums website.